Hello everyone, this is our 10th tutorial. Today we will discuss Gram-Smith method of orthogonalization and orthogonal complement. So recall that given a set which contains some vectors alpha 1 up to alpha n, those are called orthogonal. This set is said to be orthogonal set if orthogonal if alpha I inner product. So of course there is some inner product structure on the vector space. It is said to be orthogonal, this set, if alpha I inner product with alpha j, this is 0 whenever I not equal to j, and this is orthogonal, and sometimes it may be called means this, sometimes it is called alpha I is perpendicular to alpha j, because the idea comes from the that vector space kind of thing, that is 1 0, this is perpendicular to this vector. Okay, inner product of e1 and e2 is 0 in standard inner product space, and this set is said to be orthonormal if the inner product alpha I with alpha j is 0 whenever I not equal to j, but in addition we want the length inner product of alpha I with alpha I, this should be 1. Okay, and recall that the length of some vector alpha square, length or norm, whatever you say, norm square is defined by alpha I comma alpha I. So you alpha comma alpha, inner product of alpha with alpha. So you need to take positive square root to define norm. Okay, so the question is, can we given a collection of vectors alpha 1 up to alpha n, and I should also mention that orthogonal set is always linearly independent, because you always see that if you can write as combination, this kind of combination, sum of ci alpha equal to 0, then just take inner product with respect to alpha j, apply alpha, this kind of inner product. From here you deduce that cj equal to 0, and this holds for all j, right? Because alpha I comma alpha j, this inner product is always 0 if I not equal to j by definition of orthogonality. So from here you can deduce the only term which survives is cj. So therefore cj equal to 0. Therefore we see that such kind of combination, 0 combination, is only possible when all the coefficients are 0. Therefore orthogonal sets are always linearly independent set. Orthogonal set is always linearly independent. Okay. So given alpha 1 up to alpha n, collection of vectors.
Sir, can you repeat this?
Okay. Why this is linearly independent? Suppose let us prove this. Okay. Suppose alpha 1 up to alpha n are orthogonal set. It is a orthogonal set, and if we try to consider such kind of combination, c1 alpha 1 up to c n alpha n equal to 0, let this is 0 for, let c1 ci belongs to the field such that this combination is 0, such that this is 0, ci I equal to 1 to n, then just apply this alpha I or alpha j, whatever you like. So this is 0 comma alpha j, and if you take inner product with 0, you can deduce by linearity that this is always 0. Now use the property of inner product. Yes. So if you use the property, you can take those coefficients ci common from I equal to 1 to n, and you get alpha I inner product alpha j equal to 0. Now note that this is an orthogonal set, so this term only survive if and only if I equal to 0. Okay. So we get ci norm alpha I square equal to, and there are lots of zeros. We don't care about those zeros. So from here, since norm of alpha I, okay, of course, you need to take those alpha I non-zero, otherwise you cannot conclude. Sorry, I should have mentioned. Orthogonal set, it is better to say orthonormal set is always linearly independent, but if you consider orthogonal set, you need to take non-zero orthogonal set. Orthogonal set which does not contain zero, contain zero vector. Okay. Sorry about this.
Okay, sir. Okay.
So CI equal to 0. Okay. Because 0 is always orthogonal. You can see 0 inner product of 0 with any vector is always 0. Okay. So the question is, given a linearly independent set alpha 1 up to alpha n, linearly independent, can we so can we make a base? Suppose W is spanned by this set. W is spanned by this set, span of this set. The question is, can we mm, make, can we create some basis? Can we create a new basis using S such that W is spanned by this new basis? New basis, suppose the basis is S dash such that W is spanned by S dash. So this is an interesting question because you have already seen that orthogonal or orthonormal basis is very powerful. You can write, for example, you can see that you can express any vector in terms of this orthogonal kind of basis very easily, right? You just need to take inner product and you need to find those coefficient ci alpha I dash, right? This kind of coefficients are easy to find using orthogonal basis. So it is always interesting to uh, express, that is, to make an arbitrary basis to some orthogonal basis. Okay, S is any arbitrary basis, and we are trying to make an orthogonal basis using this S. So this process, there is a standard method or the standard theorem which solves this problem. So the idea is very easy to see, and it comes from the standard inner product or vector calculus, whatever you say. Suppose this is a vector v, and this is another vector w. Then you can project this v. We are trying to create a basis which is, that is, note that those two vectors are not orthogonal to each other, but we are trying to create a new vector which is orthogonal. Okay, so the idea is you can project this vector on this w, and the projection formula is usual v inner product with w and in the direction of w, so by norm of w square, right? You know this is the, because you are projecting this vector, the projection will be this V inner product W by norm of W, but in the direction of this W, right? This is the modulus of this vector, norm of this vector, but you are projecting in the direction of W. So you, in addition, you need to multiply it W by norm W, right? This comes from that Euclidean vector space. So this is the projection of V along W, and you just subtract this from V. So this is our V minus W, right? This direction. So this is not V minus W. This cannot be possible because the origin of vector should be always, that is, vector always start from 0. So I should write this here. So this is V minus W, this vector. So from here it is clear that uh, if we choose W, so given a system W comma V, suppose this is a basis, and now you write the same W, but you just subtract this W from V, then you will get an orthogonal set or orthogonal basis in this case. So V minus V comma W norm of W square into W. So you can prove that those two are orthogonal. You just, this is the intuition. So you need to see that inner product of this comma this equal to 0, which you can easily verify. But this is the main intuition behind this. So in general, given alpha 1 up to alpha n, we want to create orthogonal basis out of this. Orthogonal basis using this old basis, using S. Okay. Can we create orthogonal basis of W using this S? The answer is yes. So in general, S is now, there are n many vectors, alpha 1 up to alpha n. So let S dash, we are trying to create some S dash which is orthogonal basis, alpha 1 dash up to alpha n dash. Then the first vector, I'll choose the first vector as the same alpha 1. Now alpha 2, for alpha 2, we subtract the projection of this alpha 2 in the direction of alpha 1. Okay. So projection of alpha 2 in the direction of alpha 1 is given by this formula. Okay. Orthogonal projection, we say. And then alpha 3 dash is same as now alpha 3, but we need to subtract the projection of alpha 3 from in the direction of this alpha 1 and alpha 2. Now there are two different vectors. We need to subtract the projection from those two, because note that those two vectors will span the same subspace as alpha 1 and alpha 2. Okay. So we are removing the component of this alpha 3 in the subspace generated by alpha 1 comma alpha 2. So previously we just subtract in this direction, but in addition now there are two directions. So from two directions I need to subtract. Okay. So alpha 3 minus the projection of alpha 3 in the direction of alpha 1 minus alpha 3 in the direction projection of alpha 3 in the direction of alpha 2. And now you can see you can clearly observe the general pattern. For alpha n dash, you need to subtract all the projection. Okay. Alpha n minus, let me say it is projection of alpha n in the direction alpha 1 up to projection of alpha n in the direction of alpha n minus 1. So there are n minus 1 many terms. Okay. So the same formula will work. Just extend this up to n minus 1 for this. So this is how you can uh, do orthogonalization of a basis. Now, what about orthonormalization? So, orthonormalization. The same story, but here I need to work more. So, S dash is now orthogonal basis. It is orthogonal basis given by the following formula. Okay, but now we are trying to create a orthonormal basis, an orthonormal basis. So here I need to normalize all those vectors. Okay, we'll divide those alpha 1 dash by their norms, right? Then you can see that if you again take norm of this vector alpha 1 by norm alpha 1 dash, then if you multiply with some scalar, then the formula is take modulus of that scalar. You know this formula. You can prove that norm of CV is same as mod C times norm V. So here we need to take modulus of 1 by norm alpha 1. But it is already a non-negative number, real number. So I don't need to consider modulus times norm of alpha 1 by this term. Okay, using the above. But you can see those will cancel, therefore we'll get 1. Okay, we are normalizing. This process is called normalizing. Divide some vector by the norm of that vector. It will simply make it unit vector. Okay, so alpha 1 dash by norm of alpha 1 dash, alpha 2 dash by norm of alpha 2 dash, up to alpha n dash by norm of alpha n dash. And this will give you the orthogonal orthonormal basis. Okay. So this is the story about orthogonalization. This process is called Gram-Smith orthogonalization. And now orthogonal complement. Assume S is a subset, C is an subset consisting some vector v1 up to vn, not necessarily a basis. It is just S is a subset of V. Then we define orthogonal complement. The notation is like this. It is called orthogonal complement of S. S, this is defined as collection of all vector belongs to V such that if we take some vector from this small s, for example, if we take W from this small s, this is 0. Okay, for all W coming from this S, capital S. Sorry. So this is the definition of orthogonal complement. So the usual thing is easy to see from where it is coming from. So this is the R3 space, that's three-dimensional Euclidean space. Here you can see that if we take 1, 0, 0, this vector E1, then the orthogonal complement of this vector is the whole YZ plane. Whatever vector you choose, all those vectors are orthogonal to E1. If you just take inner product with this any vector from this plane, it will look like 0, comma y comma z. If you take inner product with 1 0 0 this direction, this is always 0, right? By the definition of inner product, this is 0. So if you take u1 equal to this, the set is S equal to this u1 only, then orthogonal complement is yz plane 0 comma yz such that y comma z belongs to R. Okay. Similarly, if you take both e1 e2, then the orthogonal complement will be this z axis, because now we are, this is s1, suppose s2 is e1 comma e2, this set, then all those vectors, we are trying to find all those vectors which are uh, whose inner product with e1 and e2 equal to 0. So e1 means 1 0 0 equal to 0, that means x equal to 0, and similarly x y z comma inner product with e2 0 1 0 equal to 0, that will give me y equal to 0. Therefore s2 part is given by 0 0 z, where z is arbitrary. You can see this kind of vectors are orthogonal to both e1 and e2. Okay, so this is the definition of orthogonal complement. The interesting thing is that you can always, suppose W is a subspace of phi, this is subspace now, then you can always express phi as direct sum of this W and the orthogonal complement of W. Okay, this is always possible for finite dimensional case. How we can do this kind of thing? You simply, so okay, so let me define an operator, orthogonal projection operator. I am calling it orthogonal projection operator, non-standard. So EW, it is not operator, it is transformation, because transformation, linear transformation. EW, let me define EW as from phi to W. Okay. How? What is the definition of this? It is simply take the vector phi. Suppose this W is spanned by some alpha 1 up to alpha n. This is the basis. Span of this, a basis for W. Okay. Or let me write a basis for W. Then define EW phi. So we define it as projection, as seen earlier. So this is the projection of phi. This vector was phi, and this is the projection of phi along W. But now there are few many directions, W1 up to W2, etc. So here I need to add the projection along W2 also, right? In general, the formula will look like this: V comma W1, projection along W1. So this is capital W actually. Okay. Now there are n minute direction. Sorry, I have taken alpha 1 up to alpha n. So I should write this as alpha 1. V comma alpha 1 by norm alpha 1 square. Alpha 1. V comma alpha n norm alpha n square alpha n. So we are taking projection in the direction of alpha 1 up to the direction of alpha n, and we are summing all those components. That will give me the projection of v, this kind of v. So we are taking projection on this direction, projection of this direction, and adding, such that we will get a projection of this v on the subspace W. So this is our subspace, yz space is W. You can see this, the projection is given by the projects components, those kind of components. Okay, and now the interesting thing is that you can see this EW is idempotent, is idempotent. And idempotent means if you take the square of this thing, okay, so it is, we can say it is orthogonal operator, projection operator, because in this case what we can do is just change the codomain, though it sends everything, that is range of EW is W, but we can always define this kind of thing. Then EW square is defined, right, P to V, and then again we are composing from P to V. So EW square is defined and EW square is same as EW. Okay, so the observations are those kind of thing. Range or image set of EW is W, and second observation, it is idempotent. Therefore you can always write phi as, you already know this, for this kind of thing, for this kind of idempotent case, you can always express phi as uh, image of E plus, that is, take any arbitrary vector phi, you can write this phi as EW phi plus I minus EW phi. Okay, note that this belongs to the subspace W and this will belongs to the subspace of W bar. Okay, you can easily check that if you subtract phi minus this, then this will be perpendicular to any vector in W, because we have already seen from the Gram-Schmidt method procedure, this new vector, if you subtract v, sub, if you subtract these things from v, then this will be perpendicular to the set spanned by alpha 1 up to alpha n. This is already seen in Gram-Schmidt methods procedure. You can explicitly check that this element will belongs to W bar. Okay. So the main conclusion is that every vector v can be expressed as W direction W bar. So this is the sketch of the proof. You can prove. You can fill the details. Okay. So let us solve some problems using those ideas. So in this question, V is standard Euclidean space and a basis is given for this R3. Now the thing is, we need to find an corresponding orthogonal basis. We need to use this alpha 1. So let me rename those things. Suppose this is alpha 1, this is alpha 2, and this vector is alpha 3. Okay, we need to change those alpha 1, alpha 2, alpha 3 to some orthogonal basis using Gram-Schmidt method. Okay. So in this question, we need to find beta 2 only. So note that the Gram-Schmidt process will give me beta 1 is same as alpha 1, which is 2, 1, 2, and beta 2 is alpha 2 minus the projection of alpha 2 in the direction alpha 1. Okay, so alpha 2 is actually 462. Now let me calculate those things. Alpha 2 inner product alpha 1, this is 462 comma alpha 1 212. So the inner product is multiply component wise and n. Therefore 4 times 2 plus 6 times 1 plus 2 times 2, 14 and 4 18 minus 18 by, now norm of alpha 1 square, norm of alpha 1 square is same as alpha 1 inner product alpha 1. So again this is 2 square plus 1 square plus 2 square, this is 5 9 2 1 2. So this is actually 2, therefore 4 minus 4 which is 0, 6 minus 2 which is 4, and 2 minus 4 which is minus 2. Therefore the second vector beta 2 is given by 0 4 minus 2. Okay, so let me solve the second problem. Here we need to find beta 3. So recall the formula for the third vector. It is, we need to subtract alpha 3, sorry, we need to delete those part, the projection of alpha 3 along the direction alpha 1 minus projection of alpha 3 along the direction alpha 2. So we need to again calculate those things. Here alpha 3, again this is alpha 1, alpha 2, this is alpha 3. So alpha 3 is 10 to minus 6. Now what is alpha 3 inner product alpha 1? Let me calculate those things. Alpha 3 inner product alpha 1, 10 to minus 6 to 1 2. Okay, let me calculate those things directly. 10 times 2 plus 2 times 1 plus minus 6 times 2. 22 minus 12, which is 10. And now we also need to calculate alpha 3 inner product alpha 2. This is same as 10 to minus 6, and we need to multiply 4 6 2. 4 6 2. So it is 40. And norm of alpha 1 squared, in addition, norm of alpha 1 squared, okay, here I can write norm of alpha 1 square is same as, we have already calculated, this is 9. Norm of alpha 2 square, this is 4 square 6 square plus 2 square, 56, right? Okay, so minus 10 by norm 11 square, which is 9, into alpha 1 is same as 212 minus alpha 3 inner product alpha 2, this is same as 40. So 40 by norm alpha 2 square, this is 56 into alpha 2. Okay, probably some miscalculation again. 462. Oh, sorry. I have probably I have said something wrong. Just hmm. Sorry, I have said something wrong actually. Okay. There are some mistakes. It start from this. Okay, let me withdraw my word and modify this thing. Actually, I have said something wrong actually in this case. So yes, so alpha 1 up to alpha n is given. Now we are trying to find this alpha 1 dash up to alpha n dash. So the first thing is okay, but after this I need to use this. Uh, so it is okay, up to this it is okay, but I need to subtract this alpha 2 from alpha 1 dash, because the thing is that those set may not be orthogonal. The problem is that we need to use the orthogonality of alpha 1 dash alpha 2 dash to create this alpha 3 dash, such that this alpha 3 dash is again orthogonal to the previous two vectors. Okay, so the thing is that we cannot use this alpha 1 again. In this case it is okay, up to alpha 1 it is okay, you can write alpha 1 dash, but after that you, instead of alpha 2, you need to use this alpha 2 dash. Okay, so this is alpha 2 dash, and similarly you need to use projection of alpha n along alpha 1 dash up to alpha n minus 1 dash. So otherwise there will be some issue. You cannot, uh, to avoid those issues you need to modify this actually. I'm extremely sorry about this.
But Gram-Smith's process only alpha 1, not alpha 1 dash.
Sorry.
Why you say it is not orthogonal?
Yes, sorry. Okay, so first two there will be no issue, but to prove that alpha 1 is also orthogonal to this and
Huh.
alpha 2, there is this three thing is ortho, this is an orthogonal set, there will be some issue actually.
No, you check. You check it is without alpha or dash, just alpha 1, alpha 2 is sufficient. Why you put alpha 1 dash? Without that, orthogonality will come.
Okay, let me check by this example.
Mm.
Just consider three vector instead of two, instead of n. So first one is alpha 1, then the second vector is, so instead of dash let me write beta 1 up to beta n, otherwise it is making some wrong choice of notations. So let me write beta 1 up to beta n to make our life simple. This is beta 1, this is beta 2, this is beta 3. in the direction beta 1 and in the direction beta 2. Okay, so the problem is if we choose the same thing, for example, previously I chose something like this, alpha 3 minus alpha 3 comma alpha 1, then norm of alpha 1 square minus alpha 3 minus alpha 2, sorry, norm of alpha 2 square alpha 2. Okay, previously I chose this. Let us see what is the problem if we choose this. So if we try to take inner product with alpha 1, then this is same as alpha 1 comma alpha 3 minus alpha 1 comma, so you just put, or let me do here so that conjugation is not needed. Okay, so alpha 3 comma alpha 1 minus alpha 3 comma alpha 1 by norm of alpha 1 square, norm of alpha 1 square minus alpha 3 comma alpha 2, norm of alpha 2 square, norm alpha 2 comma alpha 1. So you can see that those two will cancel, those two will get cancelled, but here that will create the issue actually. Can you see that alpha 2, initially alpha 2 and alpha 1 was are not orthogonal to each other? Can you see that? It was not given. So I cannot say that this will be 0. So to deduce those two, this new vector is orthogonal to the previous alpha 1 and alpha 2. Instead of alpha 2, you need to use alpha 2 dash. Otherwise, the process will fail. You can see that. Uh, is it clear now? What is the wrong in the previous thing? Is it clear to everyone? Thank you. Okay. Issue in the earlier method. So I am using something wrong. Not that was not Gramsci. So that is why you can easily see that here I have already got some wrong kind of answer. So for step 2 there will be no issue. Therefore you should be uh, you should consider the step 3 in this manner actually. Otherwise there will be some issue. So let me rewrite that thing, though this does not matter, but for general formula I should always write this. So from here you can see that to find beta 3 you also already need to find beta 2, otherwise you will not get any new beta 3. Okay, so I have already find that beta 2 is 0 4 minus 2, beta 2 is 0 4 minus 2. So you need to take the projection of alpha 3 along beta 1 and beta 2. Okay. Okay, the first formula will be unchanged because beta 1 is same as alpha 1, there is no issue. But for the second thing I again need to calculate. So alpha 3 comma beta 2. Alpha 3 you can see it is 10 to minus 6. 10 to minus 6, and beta 2 is 0 4 minus 2. Okay, it is 8 plus 12, which is 20, and norm of beta 2 square norm beta 2 square is 0 square plus 4 square minus 2 square, which is 20. So this is actually 20 by 20, which is 1 actually. 20 by 20, 0 4 minus 2. Okay, so those two will get cancelled. It is 10 to 2 minus 4, which is minus 2, and minus 6 plus 2, which is minus 4, minus 10 by 9, which is, let me write, 1 by 9 into 20, 10, 20. 1 by 9, I can take common. Now 90 minus 20, which is 70, minus 18 minus 10, which is minus 28, and minus 36 minus 20, which is minus 56. So this is the answer. Is it clear to all of you the how we can orthogonalize the given basis using Gram-Smith procedure? Okay. So yes, here we also need to pick orthogonal basis, otherwise the same kind of issue will arise. Okay, this is what we need to do. Just a minute. Just look at the problem. Next problem. Okay, let us look at this problem. Here, uh, we need to see which of the following are subspaces of V. Can you tell me which of the following is actually subspace of V? So,
1 and 3.
yes, you are saying this 1 and 3. Okay, let us see. So, y is a non-zero vector in V. Okay, and even if y is 0, there is no issue actually. Okay, if one y is 0, there will be some issue with 2 3, but it is okay. So recall that for a subspace S containing phi, we have defined orthogonal complement S par is the collection of all vector in phi such that phi inner product with W is 0 whenever W belongs to, for all W belongs to W. This is this subset. So The interesting thing is that this S perf is also is always, even though this S may not be a subspace. Suppose this is only subset. S is a subset, but this S perf is always is a subspace. Okay. So how can we see this? Proof of this? Can you tell me how we can prove this?
Actually, it comes from the properties of inner product.
Exactly. It comes from the property of inner product. So what are the, which property you want to use? Which two properties you need to use in this case?
First is linearity, and second linearity and C into alpha, that property.
Exactly. So you need to use the linearity property. So let V1 and V2 belongs to S part. Then it is true that V1 is perpendicular to this W, this set S. That is V1 inner product is with W is 0 for all W belongs to S, and similarly V2 inner product with W is 0 for all W belongs to S. Now if we take any linear combination, we need to check C1 V1 plus C2 V2. This also belongs to S part. So if we take inner product with W, then by definition of inner product, this is same as C1 times V1 plus V1 W plus. Therefore, this is, those two are 0 using star. By star, we are getting that this is by property of inner product. Inner product. So from here, you have proved that W is a subspace of phi. Sorry, not W, S part. S part is a subspace of W. So in particular, here we are only considering this set, this singleton set, right? Instead of S, we are, in particular, we can say the same thing for this singleton set. We are taking this thing. This is the property we can use. Now, what about question option 2? One is correct. What about option 2? Is this subset a subspace of P? Where is the problem? Can you see any problem in this case?
So this property does not hold.
Yes. Which property is not holding in this case? Which property of subspace is not holding?
Then V1 V2 comma V1 plus V2 comma Y. You
Yes.
can take, and that will become 2 actually.
Exactly. That linearity is not holding. But if you see the property that 0 always belongs to a subspace. From here, can you immediately see that 2 is not a subspace? Right? 0 always belongs to a subspace. Belongs to the subspace.
0 is not there.
Exactly. So for option 2, 0 does not belongs to this subset. Suppose this is S2, so 0 does not belongs to S2. So we are getting a contradiction. 0 with 0 inner product Y is always 0. Okay. So 2 is false. Now for 3, you can see that we are taking all those x such that x inner product with z is 0 for all z such that z inner product with z inner product y is 0. So from we are taking z from which set? So note that the collection of all z such that z inner product y is 0, this is same as, it is same as, what will be this set? The collection of all z such that z inner product with y equal to 0. So note that this is perf of S. By definition, S perf is defined in this way, right? It is collection of all vector which is perpendicular to W. In our case, the only choice of W is Y because we are taking the set as singleton, right? So this is S perf. Now we are taking all x belongs to V. So this is, suppose this is S3. So S3 is all x belongs to V such that x inner product with z equal to 0. Okay. So x inner product with z equal to 0. From where z is coming from where? Which set? Z is coming from the set such that z inner product with y equal to 0. So that is equivalent to saying z is coming from S part, right? The definition of this set, by definition of S part, this set, this collection is same as S part. So this is for all z belong to S part, right? Now note that, can you see that this is the definition of S perf. So if you choose this S perf to be a new set, then this is nothing but perf of this S perf by definition of S perf. Can you see this? This is by definition of orthogonal complement. Okay. So note that we have already proved S perf is a subspace, and again if you take perf, you will again get another subspace. Therefore, this S3 is a subspace because orthogonal complement of something is subspace. Now you are taking orthogonal complement again, then you will get another subspace. So 3 is also correct. Now what about 4? Can you say something about 4? Now we are taking for all z belongs all z such that inner product of z with y. So again you can see that uh, 0 does not belongs to this set immediately, right? If you denote this by S4, then immediately you can see that 0 cannot belongs to this set because 0 inner product with some anything will be always 0, which cannot be 1. So by the same reason as 2, 4 is false. by the same reason as. Is it clear? Is this question? The answer, the solution to this question, is it clear to all of you? Okay. Is there any doubt up to this problem?
No doubt, no doubt.
Okay, thanks. Now let us solve another problem. Here, instead of Euclidean space, we are considering uh, the space of inner product space of all linear polynomial from this interval, closed interval, to real number of this form. So up to degree 1, we are considering polynomial up to degree 1, linear polynomials. Okay. With the inner product defined by this usual inner product, now we need to find an orthogonal basis for. Okay. So note that a basis for phi is 1 comma x, right? You can always write this kind of polynomial as linear combination of x and scalar 1, x plus b. So this space is generated by this basis. Now we need to orthogonalize this basis. So initially we start with alpha 1 and alpha 2. We are trying to create orthogonal basis out of this. So beta 1 is same as alpha 1 as usual. Now beta 2, that is same as 1. Beta 2 is projection of alpha 2. So first alpha 2 minus the projection of alpha 2 along beta 1. Okay. Now what is, we need to calculate those values. Okay. So first thing is alpha 2 inner product beta 1. So alpha 2 is actually x. Alpha 2 uh, is x. So the formula is this: x times qx. Beta 1 is 1. So x times 1 dx, 0 to 1, which is same as x square by 2, 0 to 1, that is half. Now what about norm beta 1 squared? So this is same as beta 1 inner product beta 1, and beta 1 is same as 1. Therefore, by definition, integration from 0 to 1, 1 times 1 dx. And this is, integration is x. So it is 1. So x minus alpha 2 inner product beta 1, which is half, by norm beta 1 square is 1. So we need to subtract this 1. So x minus half. Therefore, you can see that this is the correct answer. Now it is immediate that okay, not that much immediate, but yes, you need to see that other option cannot be, other are not correct. That is, if you, so 1 and x cannot be orthogonal, otherwise this procedure will give you the same thing. The orthogonalization will give you the same answer. So this is not orthogonal, and you can check that this is also not orthogonal, because x root 3, if you integrate 1 times x root 3, then you don't get, you will not get 0 vector. It is it is root 3 by 2. So this is non-zero, therefore 2 is false. For 3, let us see what is happening for 3 also. So again, there is some square root 3 terms, and if you integrate, you will never get square root terms. Therefore, that cannot be cancelled. Okay. So let me check, because there is another possibility of having 0 as the answer. So 1 times 2x minus 1 root 3 dx, 0 to 1. So first one will be x square by 2 minus x. So yes, the same. This is the reason. That is, you cannot cancel root 3. There will be some root 3 terms. Root 3 minus, okay, 0 to 1, 1 into 2x minus 1 root 3. So x square minus, yes, yes, it is okay. Root 3 times 0. Root 3 times 0. So this is also answered, because you can see that if you multiply this with 2 root 3, you will get this answer. So alpha is perpendicular to beta. That will imply alpha is perpendicular to c beta, right? So if beta is orthogonal to alpha, then c beta, so it is, you can think it as alpha and this as beta. Then here the c beta is root 3 by root 3, 2 root 3 times beta actually. So 3 is also answer. Though this new basis is not coming from Gum-Smith orthogonalization, but it is an orthogonal basis. We don't need to find orthogonal basis coming from Gum-Smith. We only need to find this orthogonal basis. So yes, 2 and 3 and 4 are the correct answer. Is it clear to all of you? Okay, great. So let us see the next problem. Here there are lots of inequalities, and we need to see which of the following are correct inequalities. Okay. Uh, in this case we'll use Cauchy-Scourge inequality. We already know yes. Cauchy-Scourge inequality for an inner product space. We already know there is some inequality, that is inner product of alpha with beta, the modulus of this, so that this becomes a real number. This mod is always less equal to norm of alpha times norm of beta. Okay, where alpha and beta coming from some inner product space. Now, can we use this to prove this kind of properties? Can you see an inner product from this kind of integration?
Inner product x comma f of x.
Exactly. Uh, Integration of, yes, exactly. So let us consider the inner product on the vector space of real valued function v equal to vector space of this of real valued function on 0 1, of course. So real valued functions on 0 1. Okay, so we define the inner product by this f comma g is 0 to 1 fx times, it is real valued, so we don't need to consider bar, fx times gx dx. Okay, this is the inner product which we'll use to prove such kind of inequalities. Now, instead of g, we put f, and instead of g, we can assume x. So let g equal to x. Then we'll get, then using star, we'll get mod of f, this inner product, norm mod of this less equal to norm of f times norm of g. Okay, by star, by Cauchy-Squar's inequality. Now this equal to x times fx dx, right? We are just multiplying fx and gx, which is x fx. Modulus of this is less equal to norm of f. By definition, this is square root of. So what is norm f square? Norm f square is same as inner product of f with f itself. So this is fx times fx, which you can write mod, but it is not important. Fx times fx is always positive, non-negative, because real valued function is given. So mod fx square times dx. Okay, so this is the norm of f. Now what about norm of g? Let us calculate norm of g. So by definition, this is integration norm g square is same as integration 0 to 1 x times x dx. So g times g dx, which is x cubed by 3, that is 1/3. So we can write 1/3 here. Okay, but of course we need to take square root of this, positive square root, to get norm. Okay, therefore just we are getting f xf x dx 0 to 1 modulus of this is same as fx square by 3 dx half of this, square root of this. Oh, sorry, integration, of course, 0 to 1. So which of the following is correct? Can you see that uh, which will be correct in this case? So we get this thing is less equal to 1/3 of this, but it is always true that 1/3 is less equal to half, and half is less equal to 1, right? Therefore, from here, this will be, this term will be less equal to fx by 2, fx whole square by 2, 0 to 1 dx to the power half. And this is, half is less equal to 1, so 0 to 1 mod fx square dx and to the power half. So can you see that option A and B both are correct. This is easy to conclude. Now, what about C and D? Can you conclude about C, D? So, 1/4 less equal to half. Now, can you say that is there any possibility of having this kind of inequality? So, using Cauchy-Squarge inequality, we can prove those two, A and B. But what about C? Is there any other method by which you can conclude C and D, C or D? So recall that Cauchy-Squarge inequality does not stop here. It also says something, right? It also says equality appears when, if and only if, not when, if and only if alpha, beta are linearly dependent. So from here, you know that there can be possibility of equalities, right? So let us see what happens when fx equal to x. So by Cauchy-Squarge inequality, Cauchy-Squarge theorem or inequality, whatever you say, in addition, we conclude that this, instead of inequality, there will be equality if we assume fx is a scalar factor of x, right? So x times fx dx 0 to 1, this will be same as this one, mod fx square by 3 dx to the power half. You can also explicitly check. Sorry, it is not needed because yes, fx, if fx equal to x, it is direct, immediate. Okay, so we can use this thing, and now you can see that this inequality you cannot. This is the surfaced kind of inequality. Uh, you cannot produce this kind of thing. So if you divide by 1/4, if you divide by 1/4, 0 to 1, this dx, you can see in general this is strictly less than. Okay. So you cannot say that this is less equal to this, because we can find some counter example. If we choose fx equal to x, this can never be less equal to this. This is always strictly greater than this thing. Is it clear? So those two are not actually correct. Okay. C is false, D is also false. Because C is false, therefore D is obviously false by the same reason. 1 by 8 is less equal to 1/4. So if this is not possible for, sorry, D is false implies C is false. Okay. C is false implies D is false. Okay, sorry, confusing. So is it clear to all of you up to this problem? Let us move to the next question. Okay. Here we are considering standard Euclidean inner product on R3, and we are also considering a subspace W given by this, some diagonal kind of subspace, straight line. Now if beta equal to this, then what will be the shortest distance between beta and this subspace W? So this is a vector beta, and we are considering a subspace W. Suppose W is this line, means W is the subspace given by this line, straight line, and we are trying to measure the shortest distance from this B. Shortest distance means from here we need to find. So let me define what is the shortest distance. Distance beta comma W, it is defined by norm of beta minus alpha, minimum of this norm. Okay, this is minimum, means infimum will attain, so we can write minimum also for all beta, for all alpha in the subspace. Okay, so we need to see all the subspaces, all the alpha 1, alpha 2, alpha 3, and we need to find the uh, smallest beta minus this alpha, non beta minus alpha. Okay, so this is the distance between those two things. So can you see which will give you the correct distance, which vectors, which alpha 1 will give me the correct distance? So from geometry it is easy to see that if we choose this one, so this, if this this is the subspace W, if we choose the projection of that is complement of W, if we take projection of beta on W curve, this one, then that should give me the correct choice of this alpha for which infimum will act. This is the rough idea. You need to prove that this is the smallest possible, this choice is smallest by using triangle inequality, this kind of thing. Okay, so this is the idea that the small, the shortest distance is given by, this is actually same as, so if we take this to be alpha, then beta minus alpha 0, that will give me the distance. Sorry, alpha 0 is projection of beta on W, then this beta minus alpha 0, this is my alpha 0, projection of beta on W. We already know the projection formula, beta alpha 0 by, so this beta minus, sorry, this is projection of beta along the space W, this is W. So we need to subtract this projection from this beta actually. Okay, we are projecting the vector beta on the subspace W, and we need to subtract from this. Okay, so let us rewrite the whole thing. The projection of beta on W, it is given by the formula beta minus. So you can see that W is spanned by this set, this basis 1 minus 1. We can choose this as alpha, the direction. Beta alpha by norm alpha squared times alpha. Sorry, the projection is this, but I need to subtract after that. So beta is 10 4 5, 10 4 5, and alpha is 1 1 minus 1 1 1 minus 1 by norm of alpha square 1 square plus 1 square minus 1 square times alpha 1 1 minus 1. Therefore 49 by 3, which is 3 times 1 1 minus 1. So this is the projection of beta on W, but now this is the projection, but I am trying to find this distance. So beta minus alpha. So I know that infimum will attain for this particular alpha 0 for this projection, but I need to find explicitly what is the norm of beta minus alpha. So norm of, let me denote this by the notation EW alpha, projection of alpha along W, this direction. So beta minus EW alpha. This is actually 3 3 minus 3, and beta is 10 4 5. So 10 minus 3 is 7, 4 minus 3 is 1, and 5 minus 3, which is 8. So norm of this. Fifty plus 64, so 114. Okay, we need to take square root. This is the correct answer. Is it clear to all of you how we can find this kind of distance? So this is the definition of distance, but you can prove that shortest distance will be given by the alpha, where alpha is actually projection of beta on the surface W. Is it clear to all? Okay, so let me do the next problem. Here, uh, we are considering inner product space, standard inner product, and W be the subspace of W be a subspace. Uh, this is the projection, orthogonal projection E from P to onto W. So we are projecting the whole vector space on this W. We need to find W per the orthogonal complement of this W. Okay, so we have already seen for this kind of orthogonal projection, the V can be decomposed as W plus W per. And moreover, we can, if the orthogonal projection is already given, then this thing is actually same as this is range of E. We have already seen that every vector can be written as EV plus identity minus EV. But here we write E from V to V, otherwise addition with identity will not make any sense. So, therefore, this W is actually range of E, and this W per is coming from range of I minus E. Identity operator minus E. Okay, so we can use this to find orthogonal projection W per. So, just okay. Moreover, I should say that orthogonal projection on W per, it is actually given by this projection formula. It is actually I minus E from P to P. That will give me the projection on W per, and E will give me projection on W. So E is already given. We need to find projection on W per, which is same as I minus E. So here the projection is denoted by M. So M of x, y, z is same as I minus E on x, y, z. Now identity on x, y, z is will give me x, y, z, same x, y, z. But E on x, y, z is given by this formula star. So x plus y by 2, x plus y by 2, and z. Subtracting will get uh, x minus y by 2, then y minus x by 2, and 0. So from here you can see that uh, this is the correct answer actually. A. Right? No. Okay. So, so this problem is similar. You can easily try. You can easily solve this problem. Just use this thing that range on W perp is coming from this projection I minus E. You will get the correct answer. Now let us solve this problem. Here V is finite dimensional inner product space, and alpha 1 up to alpha n is orthonormal basis for V. T is linear operator on V. T maps V to V. A is matrix representation of T. Okay, recall what is the matrix representation? So A is matrix representation of T. That means if we apply T on basis element T of alpha I, that is same as AJI alpha j, right? It is by the definition of matrix representation. This is how we get the matrix representation of transformation. Of course, AJI are actually the component of the matrix, n by n matrix. So in our case, we need to find those coefficients. Okay, we need to find ARS. Here, the thing ARS is used. Okay, so I should change instead of. Okay, let me rewrite T of. Okay, it is okay. So taking inner product with alpha j, what will we get? Or instead of alpha j, let me write alpha k. So we'll get t alpha I comma alpha k is aji alpha j alpha k j equal to 1 to n. Note that this is orthonormal, right? So first I use the property of inner product, then this will becomes alpha j comma alpha k j equal to 1 to n. Okay. Now by orthonormality, this term will survive if and only if this index j is same as k. So this is nothing but a k I times 1, and all the other terms are 0, right? So from here the conclusion is that aki is same as t alpha I comma alpha k, and instead of aki I am writing ars. So ars is same as t alpha s. This is the correct answer. Is it clear to all of you? So note that if you this is sorry if you exchange those two things which is given here, then there can be some issue, because we don't know if it is over real number or not. In general, if nothing is given, we assume it is over complex number. So if we assume this V is a vector space over complex number, then A is correct but D is not correct, because this is conjugate of this. So A is the only correct answer. Is it clear to all of you? Great. Okay, this problem you can try. Let me solve the last problem. Here, the inner product. So we are considering continuous function on the interval minus 1 to, that is, we are considering all this kind of function minus 1 comma 1 to r, and the inner product is the standard, that is usual inner product. Given that w is a subspace, w is the subspace of all odd functions. So recall, a function is called odd if f of minus x is same as minus fx for all x in the domain, for all x belongs to minus 1. Then what is the orthogonal complement of w part? Okay. Uh, can you guess what will be the orthogonal complement of this w? So
All even functions.
all even functions. Yes, and this way is the correct answer. Let us see how we can prove. So first we need to see that all even functions are orthogonal to all odd functions. Okay. So claim, first claim is all even functions, that is actually subspace of this w part. Okay. So if we choose an even function ex, we need to prove, let, instead of it, let ex be an even function and ox be an odd, respectively. Then we need to prove that E comma their inner product EX OX. Okay, sometimes I am putting OX. Whenever I am putting OX, I am denoting it same as O, and this is same as the function E. I am not evaluating on a fixed X or fixed, yes. So that should be clear. So this inner product in this vector space is given by the integration -1 to 1 ex times ox dx. Now we'll change, uh, we'll use the change of variable. So let u equal to -x, okay, or t equal to -x. Then the range will -1. So when x equal to -1, t is 1. So range will be flipped, and e of x is e of minus u.
Even function into odd function is odd. Integral -1 to +1 odd function is 0.
Yes, yes, you can directly conclude that. Exactly. Okay, let me complete this. D of this is -1 times du. So for even function, you will get this eu same as eu, and for odd function, o of minus u is same as minus of ou, but minus minus will get cancelled, so ou du. Therefore, this one is same as minus of the same thing. That is, if we denote this one by k, this is same as minus k. So k, when k is same as minus k is same as minus k if and only if k equal to 0. That is 2k equal to 0, and we are considering field is real or complex, then this is true if and only if k equal to 0. So from here, the conclusion is that 1 is 0 and 2 is 0, therefore ex, this kind of inner product, is 0. Okay. So from here, it is clear that all even function is perpendicular to odd functions. That is, all even function is contained in W form, the subspace of all odd functions. So even functions, subspace of even functions is contained in W part. Okay. Now we note that you can always write, we can always express any function as the standard trick fx uh, plus f of minus x by 2 plus fx minus f of minus x by 2. And note that this is actually odd function, this is even function, this is odd function. Therefore, the conclusion is that vector space V is direct sum of, this is the set of all odd function is denoted by W, W plus the set of, let me denote the subspace of even function by some, let me denote it by W1. Okay, so WE, so W plus WE, let's say. So now can you see the conclusion now immediately follows, that is, this cannot be possible, that this is a strict inequality. From here we can say this is now equality, because if it is strict, then there is some even function, there is some function which is not uh, sorry, okay, suppose there is this is a strict inequality, then there exists some function fx which is not even, but fx is perpendicular to w bar. But then from here we can say that this function comes from the complement of we, right? So which is a contradiction. Because we are considering complement. So from here the conclusion actually follows, because you can see that if there exists some even function, there exists a function f which is not even function, but f belongs to w power. Therefore, f belongs to w power. Therefore, f cannot comes from yes. Uh, if we write f as combination of some w e, some function, even function e plus some odd function, it is not possible, because this coefficient must be 0. So there should be 0 because it is coming from part. Okay, you cannot take a non-zero odd function. So this function always come from this even. Therefore, we are getting a contradiction. So this is the general method. That is, you just prove that whatever your guess, that is a subspace of W per, and now prove that this subspace, if you take this subspace, and if you take direct sum with W, that will give me the whole space. From here, the conclusion immediately follows. Otherwise, by the method which I have discussed, from that method we'll get a contradiction. Okay. So from here, the conclusion is W is actually W per. So the set of all even functions. This is the correct answer. And those are actually false, because you can always uh, make, so this is a strict subspace of even functions. So this is false. C is false because you can produce lots of functions which are not even, but it satisfies this property. And D is also false. That is the same kind of thing. So is it clear, the solution to this question? Okay, great.
Yes, sir. Yes.
Nice. So let me stop here. If you have any questions, you can ask. Is there anything you want to ask?
No, sir.
Okay. If there is no further questions, let me stop here, and thank you for attending.